Professor DeSimone is a Sangambir Professor of Translational Medicine and Chemical Engineering at Stanford University, where he is also in the departments of Radiology, Chemistry, and the School of Business. We are very fortunate to have DeSimone here today to speak to us because he is an incredibly clever and creative scientist. He's made paradigm-shifting contributions to many fields, including green chemistry, medical devices, nanomedicine, and 3D printing is what we're going to hear about today. He also co-founded several companies based on this research, and this includes the additive manufacturing company Carbon. And if you've seen Adidas sneakers at all lately, you know about this company, but they do a lot more than sneakers. For his work, DeSimone has been recognized by too many honors to count. And I just want to highlight, for example, including the National Medal of Technology and Innovation. That's the highest honor in the United States for achievement in leadership in advancing technological progress, and it was given to him by President Barack Obama. He's also been elected to all 3 of the US National Academies, showing the breadth of his abilities in research. DeSimone is also a fantastic teacher, as I've witnessed firsthand. So it's terrific to have Professor DeSimone be the last speaker of the summer school. Joe, welcome. Thank you so much for coming.
Thanks, Heather. It's terrific to be invited and to be introduced by a former student in my class who obviously has elevated way beyond anything that I did. And so, Heather, congrats on your career.
Thank you.
And it's nice to be here with you all. And it's nice to be in California too. I sort of been on the East Coast most of my career and grew up on the East Coast, and my wife and I are long on California, so we love both being down in Southern California and the Bay Area here. So appreciate the invitation, and thought I would share with you the emerging team here at Stanford. A great group of students, graduate students, undergraduate students, master's students, a couple of postdocs, a few physicians, and some of the staff. And you know, I think, you know, the one point I wanted to make is that the students are gathering from, the trainees are gathering from lots of different departments in the School of Engineering, of Bioengineering, Materials Engineering, Mechanical Engineering, Chemical Engineering, Computer Science, Chemistry, in the School of Humanities and the Sciences, and we think a lot about entrepreneurship and GSB and the like. And it's a really great group coming together, and you know, we think a lot about our culture and our values, and something we did a lot both at North Carolina and at Carbon. This is I'll talk about some of the things we're doing in 3D printing, and just pointing to you know, a lot of the people behind the scenes that are leading what's happening in additive manufacturing. And Carbon is an amazing organization, and was fun to lead them for a period of time. And now chairman of the board, and Alan Coleman, former CEO of DuPont, has taken over as the CEO. But I think in a lot of things, I want to start with this slide. You'll see this up on our website. You know, in this day and age, I think it's really important for everyone to be really clear about their values and what's important to them and you. And when I've always found that once you're clear about your values, that you become a destination for excellence wherever it is. And so this is really important. You know, people at the end of the day is all about, or organizations is all about people, and what you stand for, what you want to be motivated by and for, and we want everyone to be clear that these are the things that are important to us. And you can read more about this on our website. And part and parcel of that is, like a lot of people in the audience here, we think a lot about innovation. And I love this quote from the former dean at Harvard, Henry Rosofsky. Research is an expression of faith and a possibility of progress. The drive that leads scholars to study a topic has to include the belief that new things can be discovered, that newer can be better, and that a greater depth of understanding is achievable. Research, especially academic research, is a form of optimism about the human condition. And you know, nothing reinforces that more than the times we live in today, between COVID and the social media challenges, national security challenges, all sorts of things, work environment. medical devices, all these things are energy. Everything's really important right now. And it's never been a more important time for scientists and engineers to be contributing to the well-being of society. And we're inspired by those things and that call. And over my career, we have been thinking a lot. We're a polymer group at our core, and so we think a lot about synthetic organic chemistry. And our sort of bent on that is sort of a chemical engineering aspect of thinking about novel processes. Throughout my career, we've always tried to do synthetic polymer chemistry in unusual ways and unusual media or unusual reactors, if you will. And a lot of this started with our work in liquid and supercritical CO2 to do fluoroolefin polymerizations, where we show that you can do free radical chemistry in CO2. And it was not only chemically inert, but because of low viscosity and high density and diffusion control reactions, you could do some amazing things and make high quality products. We could design surfactants that can self-assemble in CO2. And as you change the density, you can change the degree of self-assembly. And this whole area turned out to be really important from an environmental stewardship point of view, because a lot of the fluoropolymers that you're aware of today have historically been made in water, which is interesting. You got one of the world's most hydrophobic materials on the planet. You're going to make it in water, and you need a special detergent to do that. Those detergents, those surfactants known as PFAS, are persistent organic pollutants and are causing lots of havoc. And this has been the slowest train wreck I've ever witnessed from an environmental point of view in the PFAS issues. But CO2 allowed us to eliminate that. And that was a really interesting run for us. And part of that too was designing liquid forms of Teflon, perfluoropolyethers, which we are really experienced at now. These are fluorocarbons that are very oxygen soluble, and they can be chemically functionalized. And we started functionalizing them into the microfluidics world in some collaboration with Steve Quake when he was down at Caltech before he got to Stanford, making some microfluidics that were resistant to swelling by organic solvents. So in fact, there was just an interesting paper from the Beast Institute yesterday I saw on the web about PDMS and the partition coefficients of organics in the silicone microfluidics. And then we were watching what George Whitesides was doing in imprint lithography and the swelling of organics and silicones there. And we started using these liquid fluoropolymers as an alternative to silicones, just like we did in microfluidics. And then we realized that we could actually start molding particles in these imprint lithography. And we developed in these imprint lithographic molds, and we developed the technology we refer to as PRINT, particle replication and non-wetting templates. And so this whole idea in a roll-to-roll process that we could have a mold almost like an ice cube tray from the micron scale down to the nanoscale, and we could fill that unique cavity to make a reactor out of it on that length scale, chemically convert the liquids into polymers, and then we could then remove those particles as particles with controlled size, controlled shape, and most importantly, controlled chemistry. And not only controlled chemistry, but spatially trying to control where certain chemistries were within particles. And this whole area of functional colloids and putting these kind of particles into new environments and the like was a fun run. And we started to realize that as the microelectronics industry was making things smaller and smaller, that from tens of microns to fractions of a micron, it really started to get into the realm of medicine and viruses and bacteria. And so now there was basically a convergence of the lithographic tools of the computer industry down to the length scales in biology. And this set us up for really thinking about exploiting these particles in life sciences. And there's really interesting, when you think about molecular approaches, bottom-up self-assembly, there's a lot of amazing chemists, amazingly clever chemists that are running in this world here and doing things that is just stunning for me to watch. This looks harder to me, and you have to be really clever. This is where a lot of people play. We're playing over here. The top-down fabrication approaches I've always appreciated as a different view, but this area, they're crossing in this length scale. And so I love this approach, and I wish I was competitive in this approach, but there's way smarter people in that world. And the company that spun out of the lab is on the NASDAQ. Is a pre-revenue biotech company that uses some of these imprint lithography techniques for making mostly in meter dose inhaler dry powder systems. But other things we started to do. These fluoropolymers we found out were miscible polyethylene glycol. And then we started realizing polyethylene glycol will dissolve lithium and lithium salts. And we started exploring the opportunities for non-flammable batteries based on these approaches. And we spun out a company called Blue Current with Natasha Balsera. Blue Current's up and running and gotten into basically solid state batteries based on elastomers. Very exciting field based in the East Bay here. And then these fluorocarbons that we were making in CO2 became the foundation for what I'm going to talk about today, and the foundation for carbon. And that's having a special window that's not only optically transparent, but also permeable to oxygen, and the basis of the company, carbon. So that's sort of my career in 2-3 slides. But there is a method to the madness in here. And it's sort of, you just see how the evolution of that, looking back 30 years for me now on that. So let me talk a little bit about 3D printing. Obviously not a new topic to everybody here, a lot of excitement in the maker community, democratization of manufacturing or fabrication, really, really powerful. But you know, it's arguably been a prototyping technology, and for the most part. And if you look at the polymer-based versions of this, you sort of have the extrusion approaches, also known as FDM, where a material basically is extruded out of a nozzle, kind of like a hot melt glue gun, rastered across the surface. Big breakthrough in that area. And then there was another area of powder diffusion or powder fusion. Selective laser sintering as an example. This, in metal world, this was done a lot. In polymer world, it's being done. But you know, metal powders, when they're sintered, they're atomic solids, and with a high surface tension. So you melt two particles, they flow together. But as you know, polymers, there's no entropic forces for mixing, essentially. Low surface energy, and diffusion is really on a long length scale, especially at the high molar mass. And polymer properties are all derived from chain entanglements. And when you transiently heat something up for a short period of time, you don't evolve the chain entanglements like you do in convective injection molding like processes. But nonetheless, it's gotten some traction for sure. Binder jetting is another example, and polyjet, you know, deposition approaches. And then there's a SLA, a liquid-based photo curing process. So this is one way of thinking about the lion's share of the 3D printing world. Not to say that there's not things lying in between here, and there's lots of great opportunities, exciting things happening in literature. This is what extrusion technology would look like. Everyone's pretty familiar with FDM and MakerBot and Ultimaker and others. This is a powder fusion approach. This is, you're gonna see a blade moving a polymeric powder back and forth, and then you'll see a laser hit it. And then the laser makes a pattern. And this is actually getting pushed into the table layer by layer, and then you'll see this block of powder come out. And that's what SLS looks like. You know, you have you intrinsically have a block of powder, and you intrinsically have your parts supported and embedded in that block of powder. And then you have to go in and get your parts out of this block of powder. And some aspect of these powders are reusable for sure. But you can see you have to deal with the powder. And if you have a lattice and all those things, you got to get all that powder out of there. But most importantly, because of the high molecular weight and the fact that polymers properties are derived from chain entanglements, you could crack open these products made by this laser sintering, and you could see the deposition of particles layer by layer. And in fact, you can see the whole particles. They're barely blended in. And that's because of the transient nature. People are trying to go fast, and you have a lot of porosity, and you don't have the full maturation in the chain entanglements between particles like you do at the center of a particle. The photopolymerization approach, SLA, this is a version I'm going to show you from bottom up, where the laser light's going to hit from the bottom. It could be a LED or laser. You basically sandwich a thin layer of liquid between a platform and a window. You irradiate a two-dimensional pattern cure that liquid, and now you've cured and made a pattern, almost like lithography, in positive lithography. And then you have to make the next layer. And so somehow you have to delaminate that from the surface. You have to bring in more liquid. You have to reposition the part and do it again and repeat this over and over again. So this is not so much it's an adhesion issue. It's two things. It's an adhesion issue and it's a mass transport issue. How do you get monomer back in there? It's not just an adhesion issue. A lot of people in the literature are forgetting that. It's an adhesion issue and a mass transport of new fresh monomer. I think all of these processes are more akin to 2D printing over and over and over again, rather than 3D printing. And I think 3D printing is a slow process traditionally because of the layer by layer approaches that leads to anisotropy. Because of the particles or layers that are not fully fused leads to that, it results in that anisotropy. And the material choices, especially for light-based polymerizations, have been far too limited. And so in many ways, the team was intrigued. We were intrigued by this image of T1000 and Terminator from Judgment Day. But the idea was, could we have the mass of an object be derived from a puddle of liquid underneath it? That's the physics we were interested in. Could the mass of the object be derived from this puddle of liquid coming in underneath it as we grew parts? And in that regard, we developed a process where we would use a light-based process and using 385 nanometer light, LED digital light projection system through a very special window that was not only optically transparent, but would be permeable to oxygen. And so what will happen is we lower a platform, and that very first layer that we would bond to this platform would bond to the platform, but not to the window, because oxygen is an inhibitor of free radical polymerization. And so what happens is you lower this platform into this liquid, and we're going to make this object on the left. You'll see this two-dimensional pattern of light get turned on here as soon as it gets close to the window. And then we're going to basically play a movie. And so this object is being lifted up off the window, but it's being done in a way that there's a gap between the growing part and the window. And that gap of liquid, the puddle, like the Terminator, is being sucked in underneath the part by suction forces as the object is being pulled up. And so the resin renewal, the flow of liquid into this gap, is the essence of this. And a gap provides the resin renewal for the growing image, the growing object as things are taking off here. And so walk through some of these things. The window is back to that fluoropolymer, a Teflon AF type material, optically transparent, very permeable to oxygen, very chemically and photochemically stable. But you've got to think about, there's a lot of forces, adhesion forces, as you pull the object up and you're sucking liquid into that gap. And so the window can drum, and this works well for small areas, but you've really got to be thinking about the window. And is it a stiff window is really needed in order to have liquid be pulled in and the window doesn't deform, because you'll deform the object. And if the window is a liquid window, there's some reports of that in the literature, liquids are more deformable than films are, and it can get pulled up into the part and can be problematic. So it's not just an adhesion issue, it's a mass transport of the liquid underneath. And let me show you that. This is an optical coherence tomography image showing you the liquid being drawn in as a river as it runs into this part. And that liquid's got to get to the deepest pixel at any given cross section as the surface area is changing in contact with the window. So it's a mass transport issue. And we study this a lot. And so if you just look at this from a polymer chemistry, polymer physics point of view, what's happening here on the z-axis, we're going from the window surface up into the liquid. And this is a generic concentration axis where the window is here. And so what happens is, as light comes through the window, the intensity of light as it exits the window and goes into the liquid reservoir above it, the intensity of the light is at its highest as it exits the window. And then its intensity will decrease with distance just through molar absorptivity, right? Or scattering. And that light is creating radicals. And so the concentration of radicals in a free radical polymerization, because the resin's formulated with a photoinitiator, The radical concentration will basically track with the light intensity as a function of distance. But we all know in free radical polymerization that we're classically trained. If you want to do a free radical polymerization, you degas your monomer. You're doing it because you're removing oxygen. And we count on oxygen active inhibitor, especially during shipping of resins, so that they don't prematurely polymerize. So we're not removing the oxygen and during this free radical polymerization, but the light, as the light decomposes a photoinitiator, generates a radical pair. That radical pair, the rate of reaction with oxygen is far greater than the forward initiation of the polymerization. So what's happening is the photoinitiator is consuming the oxygen, but the oxygen being replaced asymmetrically at the window surface. And so the oxygen concentration is high at the window, and it's decreasing with distance up into the liquid like this. And once the oxygen concentration gets below a certain threshold, then a polymerization will take place. And bond conversion go high, viscosity go high, and there's this polymerization gradient. And there's this gap that we call the dead zone. And it's this dead zone that allows resin to be pulled in underneath the part. So we do a lot of modeling and simulation. This is a really rich and exciting area where you're modeling fluid mechanics, the mechanics of the part, reaction kinetics, thermal heat evolution. These are exothermic polymerizations. Every 10-degree change in temperature, reaction rates double, viscosity changes. There's a lot happening, and a digital twin is really critical for monitoring this. But if you look at these processes, making a test pattern. I love this little study we published on. That if you're making this test pattern and you're going to make it continuously, but you can decide to slice this image in an STL model, and you can slice it every 100 microns, right? But if you're making this continuously and you got 100 micron slices of images, that means that the image is constant for 100 microns in Z. And then as soon as you reach that point, then you change the image, and then you hold that image constant for another 100 microns in Z, and then you change it again, and you change it again. Well, we could slice that image 5 times more frequently so that the image is changing more quickly. Or we could even slice it even thinner, and now the images are changing dramatically. But we're making these all at the same rate, at 40 millimeters an hour. We're just changing the images more quickly. If this were a traditional 3D printer and you change your resolution from 100 micron slices to 1 micron slice, you would slow down the printing by a factor of 100. Here, we're keeping it constant. We're actually going continuously. And with that, you can get to amazingly smooth surfaces. And there's some optical correction patterns and the like. And when we do this, but you can make some amazingly smooth surfaces using this approach. What also happens in a traditional additive manufacturing, as I mentioned, you have these layers. These layers give rise to anisotropy because of the way you can print a part in different orientations. And this is the Achilles heel of a lot of 3D printed parts, the anisotropy due to the orientation of printing. When you print free radically under a continuous manner and you fracture the part, they look isotropic to us. You can't find the images that you have. And this isotropic nature allows us to be really addressing an Achilles heel of a lot of 3D printing. So we rolled this up into a company, and we really put together an amazing product at Carbon. The founding VP of engineering at Carbon that I hired was the founding VP of engineering at Tesla. He was there before Elon got there, and a Tesla car is 100% smart hardware. It gets over-the-air software upgrades. It's a device like your phone. And we built our printer with the same DNA as a Tesla car. In other words, everything about the printer was sensored up, electrified, motorized. They're connected to the cloud. And what that allowed us to do was have a complete, almost robotic fabrication method that we could update with over-the-air software upgrades as our digital twin got better and better, and as we introduced new resins and we learned more about our process, changing the oxygen, changing the light intensity, all those things. We could do preemptive maintenance, all those things. And we launched a process. So this is basically a network effect. The more the printers are used, the bigger our network gets, the better the printing gets. That's a classic sort of tenet of entrepreneurship. And you can start stitching these printers together and start automating and going from a printer to a mini factory. And you can take this all the way, and we've done that. Let me talk about the materials for a second. Most light-based printers, and we're doing light-based chemistry, obviously, a light-based 3D printer, as you know, there's really limited polymer properties attained by light-based processing. And so we came at this with recognizing that like some of the best polymers are just reactive liquids, right? Polyurethanes, polyurea, urea urethanes, epoxies, silicones, cyanate esters. But nobody went down this path in their light-based 3D printer because, well, first of all, they're not reactive with light. And second, their printers are really slow and these kinds of liquids would gel. But we're printing 100 to 1,000 times faster with this approach. And what we decided to do was to make these reactive resins also UV curable by making co-networks. And so let me give you one example of that. So classic epoxy would be a diepoxide and a diamine. And that's would be a classic 2A, 2B, and an epoxy adhesive. But what we did is we also added some orthogonal chemistry through free radical polymerizations that are chemically inert. Notice we got the methacrylates here to avoid Michael addition issues with amines. But that we can mix all these chemistries together. We could print the part at 385 nanometer, set the shape of the part, and then have all this latent chemistry sitting there. And so this is basically a solid state polymerization in the form of a part to get amazing properties. And this works exceedingly well. You can make amazing materials. This is our RPU 130. It's a rigid polyurethane with a TG close to 130 degrees. It's very ductile. It's got impact strength that's like a thermoplastic. In fact, here's a plot of notched izod impact versus heat deflection temperature, close to a TG kind of parameter. And these are placards made by selective laser sintering. And then you hit this in the center with a pendulum or a ball and it fractures. But you do that to this material and you see ductile deformation. This is a really amazing material that's got a high impact strength, and it's made out of heavily a propane, 1,3-propane diol, polyol, 25 weight% of that in this material. You can make elastomers by extending the length of the polyol, and you can make elastomers with a TG close to room temperature or well below room temperature. So you can make elastomers that are dissipative of impacts or energy returning, depending on where you put the TG. And so what turns out is that we can now make a wide range of polymeric properties, but the details are you have to tune the resin to the printing process because of the physics of viscosity, light intensity, thermal window control. And so every resin has to be tuned to the process. And so what we did is to open up the breadth of resins, we set up basically an app store for resins. We launched a whole bunch of our own resins, but we started training chemical companies about how to design for our process so that they could learn how to do that. And then we would tune our software for their resin. And we now have about a third of the resins on the platform are third-party resins, and encourage academics to think about this is a great outlet to get resins in the marketplace. And so what's happening is that we now have a process that's really fast. They're isotropic parts. We have lots of different resins, and this sets you up for moving into manufacturing, and that's what we do. And so this idea of putting those printers together into a mini factory, where you now are not just thinking about the printing, but now you've got to mix resin at large scales, 1,000-liter totes, for example. You've got to print the part, but because of the part printing, we have excess resin on the parts. And historically, we've always just washed that in organic solvent, and that's convenient at low volumes, but that's not convenient at the million scale. And so we designed centrifuges that can spin the parts at high speeds, and that excess resin can be spun off the parts, kind of like in a salad spinner, gets collected at the bottom, and that resin can go back and be reused. So it's 100% atom efficient in that regard. Almost, not quite 100%, but almost, but you're collecting all that before you go into your post-processing steps. And so here's what a factory can look like. Here's the centrifuge. You'll see a platform coming out that's got a pair of running shoes on it. In fact, you'll see that go into another robotic system. We call that which is a splitter. And you'll see the parts being split off by a blade. And then these parts come out and they each have a barcode, sort of a QR code. And I think of every part as being alive because every part has a unique record in the cloud. Even if it's the same part, we know that every part's going to have a unique record. You know, all its born on dates and its conditions, which lot of resin, which STL file. You can do post inspection. You basically populate that record with its grades in school as you measure a stress strain curve, or you measure its mass or its optical properties. And you can even measure it when it gets come back and gets collected, and you can quantify its recyclability. So its death certificate. So all those things, really new way of digital manufacturing. And this rolls up into a new process, and we have a lot of customers that are using this in manufacturing. And I got a little video here to share that with you.
We salute all those who believe good enough is never good or enough. Those who pursue excellence for themselves and for our planet. At Carbon, we apply our craft using science and technology to push limits and realize products unmatched in performance. Our difference is one you feel, and it is light years ahead of anything else out there. You feel it in running shoes that control energy with every stride. Saddles that enhance your performance and comfort mile after mile. Helmets that increase your protection every time you take the field. Clear aligners and dentures that improve oral health and give you more than a few reasons to smile. Crafted by Carbon is a promise. It stands for dedication and focus to crafting what you and our planet truly need. Ongoing creation of amazing answers to our toughest questions. We salute the leaders, dreamers, and doers who keep creation in motion, who boldly imagine a brighter future and craft it every day.
So it's used in lots of different industry sectors, lots of different material properties driving performance, including the first 3D printed parts ever on production vehicles, new vehicles out of Detroit, bicycle saddles, helmets, dental, running shoes is a fun one for us. Launched over 2017. Now you're seeing new shoes out there, really scaling, driven heavily by performance issues and biomechanics. This is the new 4D forwards that were just launched here, coincident with the Olympics. And what's exciting for us is they're now into price ranges due to volume, and it's really just scaling. And it's Adidas has been an amazing technology partner of ours, and you can see this little video here.
All runners want to feel like they're progressing, but sometimes that's the hardest part. What if we could make every run feel like progress? This was the start of 4D Forward. Breaking forces slow a runner down. We thought, how can we turn these forces into forward motion? It took 17 years worth of athlete data, over 5 million lattices, narrowed down to find the perfect geometry. One forward cell, coded to compress in one direction only, transforming vertical pressure into horizontal force, shearing forwards so that you feel a smoother transition with every step. 4D Forward is a performance running midsole designed to move you forward.
So this is this new area of polymer science. We've all focused heavily on intrinsic material properties, but this is now the world of architected materials, where you can start having properties instilled by geometry. And you're doing it with bio-based feedstocks and all sorts of stuff. And so to me, that's a really exciting world where one product actually becomes families of products in lots of different areas. But this idea where you can have stiffness or flexibility, energy returning, energy dissipating, anisotropy by design is this new horizon of material science. And look, this is not new, so to speak, but what's new is being able to make the things that you want to make. That's the new horizon that additive brings. People have been doing this with the 2-photon systems that are direct write and are slow, and they're not scalable. And now you can make these in minutes and explore new things, vary strut thickness, vary properties and the like. So it's really exciting as you start thinking about mechanical property simulations and excluded volume interactions, or volume excluding deformation so that you don't have lattices collapsing on one another, and You think about these in separations, not only mechanical properties, all sorts of transport properties. It's really an exciting day in this regard, and we spend a lot of time thinking about that. So what's happening too is that, the classic product development cycle has been where you design in your favorite CAD tools, but when you go from bits to atoms, you enter the real world with your designs, you typically go to a prototyping technology that's not your manufacturing technology. You're typically going to a prototyping material that's not your real material. And you do all that because you have to invest in tooling that's often very expensive. It's a big investment, takes time and lots of money before you go to manufacturing. What's happening in a 3D printing world, this is another tenet I want to highlight for everybody, is that now you're designing products on the means of production. You can design way faster now, and the speed of innovation is going way faster. Forget about the speed of the printer. This is speeding product development. This is hugely impactful as we can disintermediate the product development cycle. So let me just spend the last few minutes. What time should I stop, Heather?
You have a while, so you till 2:40.
Okay, great. You never want to tell me I have a while, but I'll take it, and we can certainly do questions. But
yeah,
when I think about additive-based printing and in particular the continuous liquid interface production approach, what's the future look like? And I think it can come in three buckets. One is advances in a printing process. The other is advances in resins. And the third is advances in software. On the printing side, there's needs still to go faster. We are a mass transport limited process. We're not at a reaction rate limited process. And we're working on this. We're very excited about this area, and we'll talk about this in the future. It's also a need to go multi-material printing. And we're very excited about having different kinds of properties within the same part printed at the same time. Another really exciting area. Another one is high resolution, great opportunity, especially with the dead zone. And we got delicate structures and not having the challenges of delamination and resin renewal and adhesion issues, breaking the parts or damaging the parts at that length scale. That's a huge need. And then advances in resin, especially with sustainability, would be recyclable resins, perhaps chemically recyclable resins. And we've got some great things going on there. Composites, higher viscosity resins, filled resin systems. And I think some of those with faster printing can be tied to that. And then certainly bioabsorbable is a key area. And then water soluble too. Advances in software. Well, this is I think of what we do as a software controlled chemical reaction to grow parts. That understanding the digital twin of the process and really is the key to first print success and high resolution printing, especially when you get into multi-material printing. These get to be really complicated chemical delivery systems, but it's all software driven, and it's a really exciting place. And so a lot of it's going to be AI, inspired or guided as we go forward. The topology optimization, the architected materials lattices are really key. The connectivity and this idea that every part is this unique part because of a unique record in the cloud and a role of big data, and the opportunities for tying that to sustainability and recyclability is going to be key. And then imaging, imaging is basically free today. And because of that, with your cameras and your multiple cameras on your phones, the opportunity for bridging that and bespoke products is going to be huge. And helmets that are shaped to your head and orthotics to your feet, all going to be really, really important. But let me dive into one of these, and that's a high resolution printing. And let me tie it to vaccines, very timely topic for all of us. Microneedle delivery to the dermis has been heavily pioneered by other people. And the motivation for that is, I think, mostly shown here, where we have 2 to 3 orders of magnitude more immune cells in our dermis than we do in our muscle, where, I've got the Pfizer vaccine, that needle went into my arm, but it missed a lot of the cells that we want those vaccine products to go to. And microneedles are uniquely set up to do that in an easily administratable way. And Mark Prowsens is probably the one I think about as the industry leader in the microneedle space. And this idea of microneedle fabrication was born out of the microelectronics industry. You know, the tools of the computer industry are used to make microneedles, mostly out of silicon or laser cutting or metal deposition. Or you make a master template, which a lot of us are familiar with, a lot like the print technology. You make a master template, then you make a mold of that and you mold your microneedles. And a lot of people doing that. But your delivery and your mechanics are get tied in, and it can be challenging. And so if you look at the different classes of microneedles, you know, they come in at least 3 buckets. One would be a solid microneedle that you'd want to dip coat into a liquid or coat somehow. And then you inject those needles into the skin and just leave the coating. You know, so this is like, probably from a regulatory hurdle point of view, this is the lowest regulatory hurdle because you're just using it as almost as a needle temporarily. The needles are not left in the skin, it's just the coatings. Hollow microneedles, also like a syringe, just leaving the liquid in the skin and pulling the needle out. And then the molded microneedles or 3D printed microneedles that are not designed to be removed, but instead lodge in the skin, you know, can give new opportunities too, and probably have a higher regulatory hurdle. Not probably, will have a higher regulatory hurdle than these. So we built one of our printers with smaller pixels. You know, the commercial printer, 75 micron pixel for the M2, 162 micron for the L1, the big printer, which is 5 times bigger than the M2. But building a printer at 20 or 30 microns allows you to make these amazing structures. And things you actually couldn't make in a fab very easily. Imagine if you were trying to etch silicon, you want to systematically control the thickness of your etched silicon to make thick microneedles, different thicknesses or different heights or undercuts. You spend more time designing these things than you do printing them with clip. These take minutes to print. You can make them out of a wide range of chemistry, hydrogels, cross-linked hydrogels, biodegradable systems, even water-soluble systems. And so here's an example of polyacrylic acid microneedles that we printed. And we did it with different formulations so that we control the molecular weight that we're making. And we're basically controlling the dissolution kinetics. And I thought I'd show the North Carolina logo for Heather here. It's reminiscing of when she was an East Coaster, but
Thank you.
but different dissolution rates for controlling pharmacokinetics and getting into, you know, controlled delivery systems. And now what can we do with higher resolution and make geometries that are really hard to make? You know, this is some of our early work, struggling with some of the geometries, but you know, this is where the digital twin becomes really important. If you want to make really sophisticated things, you got to be careful in how you do this. You can really screw things up, but as you start understanding the chemistry and physics of the process, you can really open up geometries that are amazing. And we're interested in all sorts of these kinds of really neat structures. These are some of the newest ones, lattice microneedles. But the whole idea is delivery to the skin. And my group, as we did the nano microparticle world, we heavily got into the vaccine space. And, you know, it's amazing what particles did for, you know, saving us here with encapsulating RNA systems. And so, you know, we're using our print particles to trap self-amplifying RNA systems. And lots of people were in the space where you do a classic foot pad injection, and then you'd watch the vaccine traffic to the draining lymph nodes, triggering germinal centers. And we tried to spell out the design rules for particle-based vaccines, where you'd vary the size and shape of the vaccine, then the mechanics to trigger immunological responses to the lungs, to the skin, all sorts of areas, intramuscular heavily. Well, now we're using the microneedles in a similar way. And so this is an example where we're dip coating the solid microneedles, we're dip coating them and basically coating them with antigens and adjuvants in a matrix of sugar. So it's a vitrified matrix of sugar, protecting these protein-based vaccines, both protein OVA and adjuvant CPG. And in that, according to the literature, not our data, but they should be shelf stable for long periods of time in that matrix. But what's really interesting is when you do this transdermal delivery and you compare it to an intramuscular or subcutaneous delivery, we are hitting those immune cells way more effectively. And we're seeing 50 times more antibody response by delivering the vaccines to the dermis, to the interstitial fluid, where all these beautiful cells are that you want to target, 50x response. And what's also interesting is that the immunological response is different. We're seeing a much more balanced Th1, Th2 response, which is opening up both long-lived T cell, B cell responses that are different. And we're really interested in those differences because of delivering to the dermis than you get from an intramuscular delivery and what role that plays. And we're showing amazing dose sparing because of the very high amounts that antibodies we're generating. We're basically saturating out the system, generating large amounts, which means we can really reduce the dose and still get effective responses. We've moved this all over to the SARS-CoV-2 based systems, a really great a spike protein system from my colleague here, Peter Kim, former president of Merck. And we've been delivering these with the microneedles. And again, we're pegging out these mice, just about making as much antibodies as possible. And we're very excited about where this is going. So I think, I'll end on this, but, my point is we've gotten used to aqueous-based vaccine products delivered by vials and syringes that have to be cold chain stabilized. And, if they're going to lyophilize that and switch, they're going to have to rerun all these clinical trials. And in times of pandemics, that's not easy. And I think you actually should change your whole R&D program and design products on the means of delivery. You can actually go faster this way and avoid some of the issues of cold chain challenges and or at least mitigate much of it. Get into long-lived doses of prime plus boost opportunities, even have it be self-administrable where you don't need hundreds of thousands of healthcare workers, and it really opens up a new future. So with that, let me end. I'll end with just a general thought. We're making things with light, pattern light. You have to ask yourselves, where else in manufacturing is pattern light used? And the big obvious one is Moore's Law. Moore's Law has been powered by pattern light for the last 50 years, but that's 2D imaging over and over again. And we believe there's a huge opportunity for pattern light in 3 dimensions at a length scales, between 1 micron and centimeters. And we think it'll be as big, if not bigger, than what one does in Moore's Law. So with that, let me end and congratulate you all on your center and your mission. And thank you for including me.
Fantastic. Thank you so much, Joe. That was a fantastic talk.
Thank you.
Very informative and also very interesting. Although we do have a question from Craig Hawker.
Craig Hawker. Is that from the Hawker Nation? Is he related to that?
I think so. When is the right time for a founder, co-founder to step aside?
Well, that's a really good question. And Craig's a world-class entrepreneur. I sort of asked him that question, but the other companies I launched, Liquidia and the biodegradable stent company, the battery company, I was co-founder, board member, hired CEOs, and but never was on the field. And I had already hired a CEO for Carbon when we launched it, and the investors asked me to lead it. And my wife reminded me how much I was frustrated by the CEOs I hired, and she's tired of listening to me and why can you do any better, kind of chiding me. So I agreed to do it for a year. I'm an academic at heart, turned out to be. I didn't know I was going to be, but I agreed to do it for a year because I told them all the reasons why it's terrible to hire a faculty member to be CEO. And they said, look, that's the way we roll out here. And it turned out to be, not 1 year, but 6.5 years. And I learned an immense amount. We raised $680 million, grew it to over 400 employees. It's an amazing business. Traded places with Ellen Coleman, who took over the CEO role. And it's hard. It's hard being a CEO. It was 24/7 for 6.5 years. And I know how hard we work in academia. I don't want to dismiss that. But when I walked into the parking lot, all I saw were car payments and mortgage payments and college tuition bills. People left Google and Apple and Facebook to come work for our company. That puts a pit in your stomach. And everything you did as CEO relied on your judgment. We don't quite have that level of accountability and responsibility. It's different. And at least it felt different for me. And so that's hard. I am thrilled I got my life back. I started getting into meetings where, we're trying to decide what's the best legal framework to choose to go into Brazil. I could adjudicate that, I think. But man, Ellen's way better at that than me. That's not my cup of tea. And so, the timing, it's hard. Any transition is hard mentally, emotionally. You hired everybody in the building. You always wonder, I suffer from the imposter syndrome just like the other person. And, can you restart and do what you want to do? And, but my whole career has been episodic, has been chapters, CO2, molding, 3D printing. I'm used to that. I thrive on that. There's anxiety with that, no question, but I enjoy it. Stanford's very different than Carolina in different ways. I don't have to build facilities here and other things, and so it's easier than it was in that regard. But it's it's a lot of work. It's expensive here, and students are expensive, but it was time. 6.5 years is a long time, and it's good to be back in the saddle.
Great, thank you. We have another question. Alexis Martel says, fantastic talk. What are some of the obstacles that your team has encountered towards making 100% bio-based resins?
100% bio-based. Well, the photochemistry is in the way. And I think that's going to be a challenge. And, I think this idea of having water-soluble fragments, low molar mass acrylic acid units that are below or that you can get through the filtration in the kidney is the way to go about this. And that's the way I'm thinking about it, is the cross-linking network side have enough water solubility and low molar mass to be excreted, and then the other components be degradable. Photoinitiators need to be compatible, all those things. Chemical degradability for recycling, I'm really excited about, and we have some good examples. And Adidas has pioneered, and I love this framework, the polyurethane economy. That's coming, right? Because polyurethanes are recyclable and chemically reversible. And I'm a big believer in the polyurethane economy. And in fact, those of you that think about recyclability, you could argue that you could snap the chalk line today and say, okay, no more technology development. There's a lot of good stuff out there. But what the society really needs, and I think you need more technology too, don't get me wrong, but you need business models. You need policies that will mandate, this common municipal waste stream, that's the problem. So when we implement recyclability of carbon, it's going to be business model driven. And I'll give you an example. Dental models, do you make aligners for Invisalign-like products? We now have versions of that where that instead of a single-use thermoset, that's a reversible thermoset. And we can take those, instead of those models are used to make an aligner. The model's made and used for about 30 minutes to make an aligner. The aligner is the product. The mold used to make the aligner gets landfill. It's a single-use plastic. That's kind of dumb. But if that were chemically recyclable, turned back to liquid and reused, and so that whole stream of opportunity, and we wouldn't have them thrown away, we'd collect them. We'd have a business model wrapped around that. We'd probably do a lease model or a subscription model and really have an avant-garde business model around it. And I think that's the future, where businesses are going to play a huge contributory role to solving the environmental stewardship problem.
We have another question that says, thank you for an amazing talk. Have you considered other light printing strategies, wavelengths, example, upconversion?
So those are neat ideas. And I think there's opportunity. There's some technology out there where people use light to create a dead zone and come in with a different wavelength of light. There's a lot of innovative things out there. And I think, we actually tried to go to photoacid generators, not photo radical systems. And then the inhibitor would be base, right? And because you have bases coming through the window instead of oxygen, and do the create it that way. Problem is, all organic liquids have dissolved oxygen in them. They all don't have dissolved amines. And so if you bring amines up to a semi-permeable membrane with an organic on the other side that has no amines, that amine will flood across the membrane and load up your organic with an amine, and then you're really fighting that. So, but anyway, my point is, I think there's a lot of really cool things to think about there, and I encourage people to go after that.
I have a question as well. So I'm very excited about your vaccine macroneedles. First of all, I just don't like shots. So this to me seems like a better alternative. But I just have two related questions. So one, so what kind of, does anybody know what kind of geometries you would need for maximal delivery of, let's say, an RNA vaccine? And then also, could you solve the problem of people not wanting to go back for their second shot by having two different, one patch that delivers it at two different times so that you could, have Pfizer delivered and only have to go once?
Heather, it's interesting question you have, and it's interesting. I went into this pandemic and this vaccine period, and in the beginning, I thought, I can't fathom anybody not getting a vaccine. I just couldn't fathom it, and there's people that don't like needles, and that's a big part of the hesitancy, I think. And I don't understand it, but I appreciate it. And so I think this is a big deal, having pain-free delivery, and so the opportunities.
Yes, thank you. It's very exciting. So I think that's the end of our time. Thank you so much for that fantastic talk. You just ended the program in a very terrific way, and I'll turn it over to Javier to finish.
Thanks, Heather.
Joe, I just want to thank you. It was a really wonderful way to wrap up the entire summer school. I thank you for participating. I think it was, really inspiring. And I think the entrepreneurship, really resonates with a lot of the components, right, that I think we need to think about. And certainly we're thinking about within BioPACIFIC. And I think you really highlighted, especially your last topic, about how we can start thinking about resin design through that full circle of coming back, of recycling and things like that. So thank you again for summer school, and share with everyone just one slide real fast. It has been an outstanding past 4 days, and really want to thank all the participants, and I want to encourage you for one last 6 minutes of your time, right? And that is to complete a survey, and you can use this link that's on this slide to access the survey. This is really important for us for two reasons. One, as we all know, right, we really want to hear your feedback. What are the things that you really enjoyed? What are the things that we can improve on? This is our first annual BioPACIFIC MIP Summer School. We'll have another one every year for the next 4 years. And so this is an opportunity for you guys to give us a little bit of feedback of what you'd like to see next year, what really worked, and where can we go from here. I also want to encourage everyone, we're going to put in the chat, and we'll also put in the Slack. We're going to have an open forum discussion as soon as I close this series. And in that, you can also have time to fill out the survey, but this will also be just a time for you to discuss anything that you want to share with us about what you've learned over the last 4 days. And again, thanks for all the participants who gave really outstanding lectures and taught everyone a tremendous amount. I want to give another shout out to Debbie and Eleni and all the other people who have been working really hard behind the scenes to have a very successful summer school. A huge round of applause. And with that, I will close our first annual BioPACIFIC MIP Summer School. Thanks, everyone. Please do take the time to fill out the survey.